Hey guys, it's Maddie. I'm going to be going over Unit 8, which is reactions that cover both chemical and nuclear reactions. So just in case some people who are watching don't know me, I just want to clarify that I'm not a teacher and that I'm not trying to be one. I'm just trying to get ready for a big test in chemistry. So 8.1, we're going to go over properties and changes. So there are two kinds of reactions. There's chemical and nuclear, and I'm not going to be going over nuclear to a great extent in the first few topics, just because nuclear is covered in the later unit. So I'm really going to be going over chemical reactions. A chemical reaction is a substance that changes into a different substance, which is different from physical properties. So we have chemical properties and physical properties. Physical properties won't change the chemical identity, so you could simply watch it, so like stepping on the scale, right? You can change the state of matter, so it's not really changing the actual substance, right? So if we have water and then we heat the water up, it'll turn to steam. But steam is still H2O. So this really doesn't change the chemical identity. So changing the state of matter is a physical property, not a chemical. And there's no such thing as a physical reaction, since, we have this substance and it's just the same substance presented differently. When it comes to physical properties, there's either intensive or extensive properties. So intensive means it's independent of how much you have, like density or boiling point. It doesn't matter how much you have, the density will always be the same, the boiling point will always be the same. Extensive properties basically mean that it is dependent on how much you have, like mass. So if you have a gallon of water and a liter of water, and you put both on the scale, the gallon of water is going to weigh more since you have more of it. A chemical reaction, on the other hand, will change the chemical identity. You're going to look for things like flammability, right? You don't know something is flammable until it's on fire. Keywords to look out for is react and form. And the substance will change. You can't get the stuff back in its original form. So here I have an example, metal rusting and then an ice cube melting, right? So the chemical property is changing here. And you can't get it back in its original form like you can for turning water back into ice. You just freeze it. You can get it back in its original form. So to conclude our short 8.1 unit, here's a check for understanding. Is density a physical or chemical property? Is corrosion a physical or chemical property? And what kind of property is melting point, physical or chemical? Now we'll be going over types of reactions. So we have synthesis, which is two or more reactants creating one product. As you can see here, A plus B results in AB. Then we have decomposition, which is kind of the opposite. So it's one reactant creates two or more products. And then we have combustion. This is generally what happens in combustion reactions. You usually have carbon, hydrogen, maybe an oxygen in there, plus an oxygen. This is required. Usually it produces carbon dioxide and water. Combustion reactions are usually accompanied by the generation of light and heat in the form of a flame. Most combustion reactions look the same, so it's really going to look like this with different amounts of carbon, different amounts of hydrogen and oxygen. So maybe you'll see C4H8O2, but those numbers can vary. But it's always going to have this same setup. Then we have single replacement reaction, which is basically an A-B swap. So you can see here that A is paired up with X, and here B is paired up with X. I try to think of this one as you have to look at the reactant that is alone as a bully, and that's going to kick out the one that isn't alone and leave it by itself. That's how I think of it. So the one that's alone doesn't want to be alone, kicks it out, and leaves it alone. So sad. Double replacement reaction. So this is just kind of like a partner swap. So A, B plus P, Q, and then, A pairs up with Q instead, and then B pairs up with P instead. So it's just switching partners. Now I'm going to go ahead and predict products of synthesis, decomposition, and combustion reactions. We'll head on to single and double replacement later. Okay, so first I'm going to go ahead and do synthesis. So we have calcium and oxygen. And this one's pretty simple. It looks exactly how it seems. So we're going to just combine the two. But then we have to go ahead and balance. So since there's two oxygens here, that means there has to be two oxygens in the products. So I'm going to go ahead and draw a 2 here. And basically what that means is we have 2 calcium and 2 oxygen. But that doesn't correspond to what's over here, right? We have the 2 oxygen, but we don't have the 2 calcium. So I'm just going to add a 2 over here, and we're balanced. I'm going to do one more over here. So we have sodium and chlorine.
So we go exactly how it seems, NaCl.
Right, because Na has a 1 plus and Cl has a 1 minus. But then we have to go ahead and balance. So we have the NaCl, there's a 2 over here, we need to balance. All right, so we have 2 sodium, 2 chlorine, but we only have 1 sodium over here. So we're going to go ahead and add a 2 over there, and we're good. So we have synthesis, super simple, super basic, just it looks how it is. Now we'll go to decomposition, and then there's 3 types of decomposition I'll go over. There's metal chlorate, metal hydroxide, and metal carbonate. So with metal chlorate, we have our metal chlorate right here, and it's going to break up into a metal chloride and oxygen. So our metal chloride is right here. So we're going to split that up.
So that KCl.
And then we're just left with the oxygen. The reason we have a subscript 2 over here is because oxygen is diatomic. Then of course we have to balance. Alright, so it looks like we're trying to get the same amount of oxygens on both sides since the potassium and chlorine are already equal. The only way to do that is we're going to have to put a 2 over here. So then that's 6, and then a 3 over here. We have 2 potassium and 2 chlorine. So then we're going to have to put a 2 over here to balance it out. Very similarly, we're going to have a metal hydroxide. So here's our metal hydroxide. It's going to break up into metal oxide and water. And our metal oxide is right here. So let's go ahead and do that. Potassium has a 1+ charge, so we're going to need 2 of them. And then an oxygen, since it has a 2- charge. And then we're going to add our water. And now to balance, looks like we just need a 2 over here. Lastly, we'll need our metal carbonate, and that is going to, so we have our metal carbonate right over here, and it's going to produce a metal oxide and carbon dioxide. So we'll write that out.
Okay.
Just like the first one, right? This one resulted in metal oxide, this one results in metal oxide, except the second reactant is different, which is going to be carbon dioxide.
Plus CO2.
And there's no balancing we have to do here. It's already balanced. And you know, this makes sense, right? Because we're taking away this oxygen, so then we're just left with CO2. So we're left CO2 over here as our second reactant. Alright, now we move on to combustion. Combustion always uses carbon, hydrogen, and sometimes oxygen, along with oxygen, to make carbon dioxide and water. So this is always going to look the same, this reaction. So except for these subscripts, those might vary, but it's always going to result in carbon dioxide and water. You know, what will vary is how it's balanced. Alright, so we've got 4 carbon on this side, so we're going to have to add 4 over here. So now we have 4 carbon, right? So we have 8 hydrogen on this side, and we only have 2. So we're going to have to put a 4 over here. We have 4 oxygen on this side, and we have 12 oxygen on this side. That means we're going to have to make this a 5 for that to equal 12. So now we move on to single replacement reactions, and yes, we are going to go back to that scratch pad so we could cover more single replacement reactions and predicting products, but first I want to go over reactivity. A more reactive metal will replace a less reactive metal. So as you can see, if it was lithium replacing nickel, it would go through, since lithium's all the way up here compared to nickel. So the more reactive, the less reactive. And if you're looking at nonmetals, you really want to use your halogens. So here are your halogens, right? It's marked up here. So fluorine is going to be the most reactive compared to subsequent halogens. So now we'll do our single replacement reactions. So first we'll check, does calcium replace silver? And we can see calcium is way above silver. You know, it's kind of important to mention that this makes sense, right? This chart makes sense that it makes sense that calcium has higher reactivity than silver, right? Because your jewelry is made of silver, right? You wouldn't want your silver jewelry to be highly reactive. So now moving on to this reaction, like we stated before, the metal replaced metal. The reactant that is alone is going to replace the reactant that isn't alone and kick it out and just bully it, right?
So it's going to be calcium, chlorine, or chloride in this case because it's
We're going to have to put a 2 right here. And then we do plus.
We're going to leave silver, we're going to kick silver out and leave silver all alone. Sorry, silver.
And now to balance, we need to put a 2 over here and a 2 over here. So basically, the standalone metal will replace the metal in the ionic compound. Now going on to metal replacing hydrogen. So notice that hydrogen can either mean an acid or water. And as said in the name, the metal will replace the hydrogen. So in this example, we'll do
Calcium, chloride. And as you remember from this example, that's going to have a subscript of 2.
And we're going to give hydrogen this subscript since it's diatomic. And now to balance, looks like we just have to do this. Now moving on to our example with water.
We're going to do calcium.
Since the calcium is replacing the hydrogen, it's really going to be attached to hydroxide. So it's going to look like this. And since we have this one hydrogen, we're still left with another. We have this diatomic hydrogen. And now we'll move on to halogen replaces halogen. So nonmetals aren't really reactive, so that's why you're not really going to see nonmetal replace nonmetal, because it doesn't usually happen. That's why it's halogen replace halogen, because as we remember, halogens are the most reactive nonmetals. So that's exactly why we'll call it halogen replacing halogen. So we can see that here's our halogen and here's our other halogen. So we're just going to replace the two. So it'll be Na
Cl.
2, and you have to remember Cl2 because it's a diatomic. And now to balance, we're going to do this. And that should be good. Now we move on to our double replacement reaction. So we'll go back to our sketch pad. And there's two types of double replacement reactions. There's a neutralization and an acid with a metal carbonate. So basically, a neutralization reaction uses an acid and a hydroxide to react and form an ionic compound and water. So that looks like it's going to be KCl. And since it's a partner swap, that just leaves it with HOH. And as we know, HOH is just H2O, since there's the two hydrogens and the one oxygen.
So we got our ionic compound in water.
Now to do our acid with a metal carbonate, we have an acid and a carbonic acid, which will in turn produce water, a salt, and carbon dioxide. So just to see that kind of play out, we have Na and Cl. We know that'll be NaCl. So there's our salt plus, and then it's going to be carbon dioxide and water. And that makes sense, right? Because we have, so these two are reacting, and then these two are reacting, right? So we have CO3 and a hydrogen. So we'll have hydrogen H2O, and then we're left with two more oxygen. So that's just CO2. So it all kind of makes sense why these products are the way they are. Now I want to talk about reactivity when it comes to double replacement reactions. What if we had sodium sulfate and sodium carbonate? Well, these would partner, and these would partner. And that would look like this. So as you can see, nothing happened at all, right? We had this here, which is now here, and this here, which is now there. It's the same thing. So if you have two elements that have one of the same ions, it just won't change. Moving on. So indicators of double replacement reactions, this is pretty simple. We just fly through this. Indicators include gas, which would be shown through bubbles. There's water, which is there's no visual indicator, but you'd have to look at the equation, and then a solid precipitate, which is just a solid forming, which is pretty clear to see. Then when it comes to solubility, if it's soluble, it's aqueous, and it dissolves in water. But if it's insoluble, it won't dissolve in water, and you could just write that as solid, right? Because if it doesn't dissolve, it's still a solid. And I'm not going to read all this, but it is on the back of the periodic table, and they're just solubility guidelines. So now I'm going to talk a little bit about ionization, complete ionic equation, and net ionic equation. So ionization is the process of a soluble ionic compound breaking up into its component ions. Soluble ionic compounds will ionize, insoluble ionic compounds will not. So let's take a look at sodium chloride, for example. So sodium chloride is an ionic compound made of ions, which are sodium and chloride. So if we put sodium chloride in water, the ions would float apart in the water, so it would end up looking like this. We've got Na with a 1 plus charge, and chloride with a 1 minus charge. Same thing for calcium chloride. Calcium chloride is an ionic compound made of ions, calcium and chloride. If we put it in water, the ions would float apart and it would look like this. Calcium with a 2 plus charge, And since chloride has a 1 minus charge, we're going to need 2 of them to balance out calcium. So this is very similar to what we're going to do in the complete ionic equation. So if we had silver nitrate and sodium chloride in a double replacement reaction, how would that look? So for a complete ionic equation, first what we're going to do is we're going to predict the products. So as we remember, these two will pair, and these two will pair. So that leaves us with silver chloride and sodium nitrate. So now looking back at our solubility guidelines, it looks like silver chloride is not soluble. See, binary chlorides, bromides, and iodides are soluble except for silver, right, and the rest. So that one isn't going to be able to be aqueous, but all the rest are. So we're going to label this aqueous. Remember, if it's not soluble, we'll just do the S for solid. So now all soluble compounds will be split up into their ions. So we have silver, which has a 1 plus, and we're going to add that to nitrate with a 1 minus. Sodium with a 1 plus. Chlorine with a 1 minus. And that's going to turn into silver chloride, since this isn't soluble. Sodium 1 plus. Nitrate 1 minus. So here is our complete ionic equation. Now we're going to move on to the net ionic equation, which is slightly different. So we're going to be taking the same thing, but we're going to remove our spectator ions, which are just ions that, don't undergo any change from pre-reaction to post-reaction, right? If you begin and end the equation with the same ions, nothing happens. So why include it in the reaction if it didn't react? And then after that, we're going to balance the equation in simplest form. So we can notice that nitrate over here and nitrate over here is the same. And we could also notice that sodium is the same on both sides. So to really understand what happened in this equation, we have to remove these from the equation. So the reaction really looked like this.
Silver, which is aqueous. Plus chloride, remember that's chloride, because it's an ion. Reacted and produced silver chloride, which is not soluble, it's a solid.
And that's our net ionic equation. Now we move on to reaction stoichiometry, which I'm also going to use the scratch pad for. Okay, this literally took me like 30 minutes to write out this whole thing, because it takes forever to write using the stupid pencil. But anyways, I really hope you guys use this because, oh my gosh, my hands hurt. Anyways, so if you forgot how to do stoichiometry, I originally did too, so I'm gonna walk you guys through step by step so we can relearn together. If we have that many grams of magnesium and it was placed in an aqueous solution containing excess silver nitrate, determine the mass of the silver metal formed. Okay, so first and foremost, we're going to write the reactants of the chemical equation from the word equation. So we have magnesium.
And we're going to add it with silver nitrate.
And now what we're going to do is we're going to predict the products from the equation, just as we've done before. This looks like a metal replaced metal, if you remember what that is.
So it's empty. And that's 3.
And then we're kicking out silver and leaving it on its own. Sorry, silver. Perfect. Now that we've predicted the products, we're going to balance the equation. And it looks like since we have 2 over here, we need another over here. And since we've added another silver, we need to balance that over there. So now that we've predicted the products, we're going to have to perform stoichiometry. So since we begin with the knowledge that we have this many grams of magnesium, we should use that to our advantage, right? Use that first.
So we have 0.0.
So now we're going to convert mass to moles. So we're going to convert the mass of magnesium we have to moles. And the molar mass of magnesium is
24.31.
Now we'll convert mole to mole. Since we're trying to find the mass of the silver metal formed, we're going to have to do 2 moles over 1 mole, since there's 2 moles over here and 1 mole over here.
Are 2 moles of silver? No, 1 mole of magnesium.
So since we've converted to moles of silver, now we'll just convert moles to mass to find out the mass of the silver metal formed. So we'll do that by multiplying this by 1 mole of silver and the molar mass of silver, which is
107.87.
And when you multiply that out, that should equal about 5 grams.
Of silver.
Now we're going to be talking about the introduction to nuclear reactions. So we're done with chemical reactions and we're moving on to nuclear. So when we're comparing or contrasting nuclear and chemical reactions, in a chemical reaction all the atoms are conserved, right? The reaction results in a movement of electrons. So that doesn't affect the identity of the atom, since identity really has to do with the protons, while electrons do with the reactivity. So in a nuclear reaction, the atomic number and the mass number are conserved. So the mass may not be conserved, but the mass number needs to be, and the atomic number needs to be, so not to mix the two up. So really, you could start with one atom and end with another, because, you don't have to start and end with the same amount of protons. And, that does definitely affect the identity. And, the driving force in nuclear and chemical reactions are the same, to reach a more stable state, but the way they approach reaching a more stable state is different. So in chemical reactions, they try to reach octet, while in nuclear reactions, an unstable nuclei will react to achieve a more stable state by emitting radiation. So you're going from a high energy state, which is unstable, to a low energy state. Then comes the question of what makes a nucleus unstable. So since we know the nucleus is very small, you can almost think of it as a blueberry in a stadium. The nucleus is very small compared to the entire atom. So when the number of protons begins to increase, it creates instability, right? Because protons, they're both positively charged, so it creates some sort of repulsion, right? So too much proton to proton repulsion results in high energy and an unstable state. So if you create more neutrons to space out the protons, that could honestly help with stability. So here's the band of stability, basically the number of protons versus the number of neutrons, right? You can see here to here. So the dots over here represent the stable nuclei. So just for example, you could see that the element with 10 protons is neon. So you can conclude that the most stable isotope of neon contains 10 neutrons, so neon 20. But as you increase the number of protons, this band of stability goes farther and farther away from this 1-to-1 ratio, right? So when you look at the element with 70 protons, you're going to need 100 neutrons to result in its most stable isotope. So really what you can conclude is that you'll need an increasing amount of neutrons to offset the effect of increasing amount of protons. And really, nuclei with 84 or more protons are unstable and will decay down into a lower number. So if a nucleus is outside of this band of stability, it will undergo radioactive decay. And radioactive decay will change the number of protons or neutrons, or both. So there are 3 types of radioactive decay. I'm not really fully going to go through each of these images. I'm just going to go over some terminology, I guess, since this is pretty straightforward. So this parent isotope is an unstable nucleus before undergoing radioactive decay. Here we have this radioactive decay. So this nucleus somehow becomes unstable and undergoes radioactive decay and will create daughter isotopes, which is just the nucleus that results from the radioactive decay. But what comes with these daughter isotopes have 3 different variabilities. So one could come with an alpha particle, which is the helium nucleus. One could come with a beta particle, which is an electron, and one can come with a gamma particle, which really isn't a particle but a photon or a gamma ray. And you can see the differences that I've listed here. So yeah, these different decays carry a separate amount of energy or moving speed with different penetrating power, as stated, is going to be highlighted in this chart. So here's a check for understanding for the introduction to nuclear reactions. How do you know whether the reaction is chemical or nuclear when an atom undergoes a reaction and attains a more stable form? And then explain how neutrons are holding the nucleus together. So now we move on to nuclear equations. As described before, alpha, beta, and gamma particles. Here's a symbol for alpha, which corresponds to the helium nucleus that looks like this. There's the beta particle, which is represented by this symbol. Really what a beta particle is an electron, and that is represented by this. And then we also have our gamma particle. When it comes to writing equations for nuclear reactions, it's actually not too bad. So we're actually going to take a look at the alpha decay for polonium. So this is the alpha decay equation we're provided with, and since it's alpha decay, we know that the helium nucleus is going to be produced, so we can write that as represented by this. So we can determine that the atomic number for polonium is 84, since, we're given the element, so we could look it up on the periodic table, and it's 84. So then we could put that down here for the atomic number. We just need to keep in mind that atomic number and mass number have to stay the same. So this atomic number has to be conserved, and this mass number has to be conserved. So to determine the element that is created as a result of this nuclear reaction, we have to subtract 2 from 84 so we can conserve the atomic number. So that would be 82. And then to conserve the mass number, we have to subtract 4 from 218, which is 214. And then the element that corresponds to atomic number 82 would be lead. So write Pb over here. And that's really it. It's not too bad. It's not too complicated. The most important thing is to conserve mass number and atomic number. And that's what we've done here. Now I'm going to be going over half-life. The half-life is the time it takes for the concentration of that substance to fall to half its initial value, which is very simple. All right, so the characteristics of half-life include that it's intensive. Intensive pretty much means, as we covered before, that it doesn't matter how much of it you have. We also learned that different isotopes have different half-lives, and we also learned that longer half-lives will have a longer curve, right? So we have this really long curve, it's the longest half-life, and the shorter the half-life, the steeper the curve, because it goes away the fastest. So here's a check for understanding. This is just applying your new knowledge of half-life to an actual question. So if you had a 50-gram sample of element Y and it decays to 3.125 grams in 48 hours, calculate the half-life of Y. Okay, now we're going to talk about nuclear applications. Nuclear fission is splitting a larger nucleus into smaller nuclei, while nuclear fusion is combining 2 or more smaller nuclei to form a larger nucleus. This chart really compares and contrasts. Both of them result in efficient production of energy, but kind of focusing more on nuclear fission, it needs enriched material, it generates radioactive waste, and it needs careful control of processes because it's very self-sustaining. And I'll get more to these characteristics once we go over power plants, which deal with both types of nuclear fusion. Has readily available reactants, relatively clean waste, but it's not feasible at low temperatures, and it's not self-sustaining. So we'll go into specific applications of nuclear reactions. So radiation therapy uses radiation to target cancer cells, so gamma rays will be delivered to the tumor. It is a fairly blunt tool, so it's pretty hard to directly target the area of interest, so that could result in killing healthy cells. Radioactive dating, so basically, if you're relating this to people, so like if you see on the news that we discovered, oh, this person was from like 1 million years ago. We did that because we're carbon-based and eat stuff like glucose to replenish that carbon. C14 is the only carbon isotope that we have that is radioactive. So once we stop eating because we die, C14 begins to decay, and the ratio of C14 to C12 goes down as we stop eating, as we stop replenishing C14, this occurs. So if you figure out how much C14 you lost and you know the half-life of C14, you can figure out the age of the artifact. And C14 has a half-life of 5,730. Something to keep in mind is that an isotope is good for determining the age of something up to 10 times the half-life. So we would not be able to determine the age of the Earth using C14, since the Earth is way beyond 50,000 years old. Now when it comes to nuclear power generation, a power plant with fission, if we look at this uranium nucleus and we hit it with a neutron, it becomes unstable, and that would result in the uranium nucleus ripping itself apart, creating 2 daughter isotopes and also lots of energy. Not only are we given 2 daughter isotopes and lots of energy, but we also release 3 neutrons. So since we're ending with more neutrons than what we began with is important, as those neutrons can hit into other atoms and create a chain reaction, so just like this picture demonstrates. So basically this is a nuclear power plant, and it's important to recognize that nuclear power plants are self-sustaining and need to be kept under control. So usually we use rods to slow down this process, but as you can see, this cycle is never going to stop. And then when it comes to nuclear power generation with fusion, it's slightly different. So basically we begin with these 4 protons, and then we undergo this fusion process and end with only 2 protons. So the good news, the pros of nuclear fusion is that, we result in this helium nucleus, which, it's clean, right? The bad news is, since we're losing protons in the process, at some point we will run out, right? This is not self-sustaining like the other power plant that we just saw. And a really, the reason why this might come across as bad news is because a really great example of nuclear fusion is the sun. So at some point the sun is going to go away and it will not be able to sustain life on Earth. That won't be for a while. We will not have to live for that, but that could be seen as a downside. Another thing that we discussed before is that nuclear fusion is not feasible at low temperatures, so imagine producing something as hot as the sun. So this is the kind of thing that we're dealing with. The last nuclear application I'll be talking about is radioactive tracing. So basically a patient will be injected with a radioactive drug, and we're able to view where the drug is located in the body as it's visible under observation. And you can see in this picture how that really goes about. And that's it for the reaction unit.